Welcome to the final lecture, number 25 in our class on stochastic processes. This final lecture will be dedicated to the introduction of some basic concepts and statements for the theory of stochastic differential equations, which is nowadays a huge theory, and it could be easily a subject of an entire class, of a semester, or even an entire year. And I want to discuss only a few very fundamental results here. We have seen stochastic differential equations already in the context of the Black-Scholes financial market model, but of course stochastic differential equations as an extension of ordinary differential equations to the case of dynamical systems under the additional influence of noise. This goes much further than just in the field of financial mathematics. As one nice example of such a model, I want to just give you a simulation of stochastic differential equation, which is modeling in a very simple fashion what is called metastability. So you could think of a dynamical system which as an ODE would be just a usual gradient dynamics for a function which for the gradient of a function which has two minima at +1 and -1. It's this function phi, and if you go by the gradient dynamics of such an equation, or plus or minus, probably I should write a minus here. If you go for the gradient dynamics of such a function in the deterministic case, you would just follow the slope of the function and would end up in one of the two minima, namely in the corresponding minimum which is closest, or to which you are attracted at the current location. But if you then add randomness to the system, you see that the behavior changes a lot. What you see is that the trajectories, of course, they stay for a while around a certain minimum, but they nevertheless fluctuate through the additional pushes, and then from time to time they change the location from being one of the minima to the other. And so if you simulate, even without at this moment having a clear concept of what you really want to understand by the solution of such an equation, but suppose you simulate this equation in a naive Euler scheme or something, then you would see probably a picture like this, which is the location of the trajectory as time evolves. So that's the time axis, and that's the location of your particle which undergoes, or which is described through this dynamics. So you see that I feel like these are the two locations where the function phi is minimal, and then you see that the trajectory really stays in one of those points for a while, and then from time to time it changes the basin of attraction, and then it fluctuates there. This is a very typical and probably one of the most simple stochastic systems which show this metastable behavior, and of course this is something that you also observe in nature, this chaotic fluctuations, so it's something that is really ubiquitous that you can observe in natural systems. And without an additional part which models the random switching between these two different fundamental states, you would not be able to give a proper description of this. So you see that such models really occur in nature, or the necessity of such models really occurs in nature, and so that's why the interest in stochastic differential equations is not of purely mathematical origin. Okay, we start by the mathematical theory, which will be quite compressed in this last session. We start with the mathematical theory by introducing our notion of a concept of a notion of a solution. So we assume we have a vector field, which would be the deterministic drift. So it would correspond to the part of the dynamical system which you would see if there was no randomness, and that's encoded in the easiest case, if you like, just by some sort of a vector field. And then you have what we should call the diffusivity matrix, some matrix which encodes the local susceptibility of the medium in which the particle moves when it is being pushed by external random forces. So the external number of external random forces can be arbitrary. That is the number d, and the whole dynamics happens in n-dimensional Euclidean space. And so this function sigma will be a function which maps a location in your state space, which is a position here, x in Rn. That position here has a certain matrix which converts exterior pushes into an actual vector. Okay, so this is just a matrix field, if you like. So sigma will be a function on Rn which assumes values in matrices, and V will be a function on state space which assumes values in the collection of directions. And then we call a pair of processes, which is defined on the same probability space, which are defined as same probability space. We call this pair a weak solution to this to a stochastic differential equation, which we write here. We call that a weak solution to the stochastic differential equation if x and omega are continuous Rn and Rd valued semi-martingales on this probability space, which is supposed to be equipped with a certain filtration. So we want that these two processes are semi-martingales such that we can use the theory of stochastic integration. And if it is so that for all times the corresponding integral equation is satisfied for these pair of processes. Here W typically will be a Wiener process or a Brownian motion in dimension D, but it does not have to be. So here in this general formulation, we assume W just to be some semi-martingale, of which Brownian motion, of course, is a particular example. And of course, this stochastic differential equation typically comes with the prescription of a certain initial value, which here in this, which we write just as an initial position in the n-dimensional Euclidean space. So X is a process which assumes values in the n-dimensional Euclidean space. That's our state space. And we have a d-dimensional additional forcing, which is this d-dimensional process W. And this stochastic differential equation is supposed to relate the pushes or the increments of this forcing in d dimension through application of this matrix into a direction, and this is then additionally acting on the motion of this particle. So that's how you have to interpret this. And what does it mean that this vector-valued stochastic differential equation or integral equation is satisfied? Well, it means that if in each of these coordinates, this is effectively to be understood as an identity of stochastic processes on each coordinate level. It means that on each coordinate level, the process, this integral equation reads that the ith coordinate of the t process, of the process x at time t, is the initial coordinate, or the coordinate I of that initial position times the stochastic integral of the ith component of the vector field integrated with respect to time against the trajectory or evaluated along the trajectory, which is an n-valued trajectory. And likewise, we have d-dimensional stochastic integrals. Each stochastic integral is driven by one of the coordinates of the driving exterior forcing process, and it is then related to become a vector or a coordinate of a vector by means of application of this matrix. So this matrix function, sigma, has matrix components sigma ik, which are then just real-valued functions. And if they are measurable, then we can, or reasonable, then we can just combine this sigma ij or sigma ik function. Or we can evaluate that at the position of the trajectory. And that's then a real-valued process, and that is integrated against the kth component, and that is and that is summed with respect to all the possible input coordinate components or input driving signals W. So if that equality is correct for all I, for all coordinates, and for all times t almost surely, then we call the pair x and omega a weak solution to the stochastic differential equation, or just a solution. And now comes an important additional requirement, which is the additional property which is sometimes true and sometimes not, that this X process is in fact adapted, and here is a misprint, if the X process is in fact adapted to the filtration which is generated by the driving signal process, then we call this process X a strong solution given the signal process omega. So if you like, you can interpret this stochastic differential equation as a mechanism that translates the signal, the exterior forcing W as an exterior process, into a trajectory that is then the X trajectory. And that would be an input-output mechanism. And whether it is actually an input-output mechanism or not, that is encoded, and I shall discuss that a little later, that is encoded by requiring additionally that not only this integral equation holds true, but also that the X process is measurable with respect to the sigma fields which are generated by this process, W. If that's the case, if that additional property is true, that we have this adaptiveness of the X process with regards to the W sigma field or filtration, then we call X a strong solution of this equation, given the signal process W. So a few remarks. Typically, of course, that's why we write the W. We will consider the case when the driving signal is a Brownian motion. It is either n-dimensional Brownian motion, or it can also be d-dimensional Brownian motion, depending on the dimensionality of this sigma field. But as I just said, is not necessarily the case. When we write W in the future, we will typically think of Brownian motion, and we will implicitly assume that we're talking about a Brownian motion process. But the theory goes beyond that. Now, why do we insist sometimes on this additional measurability condition, which then distinguishes a weak solution from a strong solution? Well, the background, for instance, you can recall what is sometimes called the factorization lemma of measure theory, which says the following, and which we then will apply to the previous situation of stochastic differential equations. Namely, if you have a certain measurable space, so for instance a probability space, so you just have some base space and a sigma field on it, and you have two random variables which assume values in certain measurable spaces, namely the z, you have a z random variable and an x random variable, and the z random variable assumes values in some measurable set with the sigma fields curly E, and you have a random variable x which assumes values in the real on the real axis with the Borel sigma field. And if it happens, or if it is so, that this x random variable is in fact measurable with respect to the sigma algebra, which is generated by this random variable z, or this map z, then, and that's now the statement of the factorization lemma, there is a function phi which maps E to x, such that this random variable x is in fact a mapping from this map z. So whenever x is effectively kind of constant on those level sets of the function z, that's what it says. So if x is measurable with respect to the sigma field generated by z, that's a sophisticated way to say that in some way the x random variable is constant on the level sets of the z function. Then it is in fact so that the x function is directly depending on the z function, in the sense that the outcome of the x function is just a function of the z function. So in that regard, in this case, the x random variable is really a function of the z variable. So we have an input-output mechanism which is then effectively in place, namely there is an input datum z and the output is x, and x has no more choice if the z is determined. And that's why we insist so much at sometimes on this measurability condition, because if we say that the solution x is in fact adapted to the filtration generated by this signal process, then by this abstract factorization lemma, this is exactly telling us that the output signal, that the trajectory that we observe as a solution to this equation is really a map. It's really obtained through an input-output mechanism. There's a direct consequence, if you like, of the input signal. And that is, in many cases, something that we want to require for modeling purposes. So we would want to see that a certain input noise generates as a map generates a corresponding output trajectory. If this relation is true, then we talk additionally not only of a weak solution, but of a strong solution to the stochastic differential equation. Get weak solutions for stochastic differential equations. We do not require a lot. There is a huge difference in that regard towards the theory of ordinary differential equations, when we typically need to require quite a bit of regularity for the vector field that we use to generate an ordinary differential equation. So I want to give an example for this, which is already a little theorem, if you like, which shows that weak solutions can be constructed kind of quite easily by means of the Gazanov transform, as we shall now see. Here's the proposition. So let V be a bounded measurable function. So very weak assumptions, just bounded and measurable. Of course, even the boundedness can be relaxed, but for the sake of the simplicity of this argument, let's even assume it's bounded. So it's just a very rough, so just an indicator function of the rationals or something, really a bad function. And let x be an initial position, then there exists a weak solution for this stochastic differential equation, which for simplicity is just the ordinary differential equation generated by this vector field V, which we know that in a general case will not be well posed or not even kind of solvable also in the sense of ordinary differential equations, so easily at least. But if we additionally perturb the thing or add noise to that equation in the sense that we have just discussed, namely in this case just Brownian motion in that dimension, so that would correspond to the case when the sigma matrix is just the identity matrix, then we have a weak solution where W is some Brownian motion. So only measurability, for instance, and some boundedness consumption is enough in order to generate or in order to show the existence of solutions to this stochastic differential equation. I want to prove this only in the case when the dimension is 1, because then I will not be distracted by technicalities which are not the essential part of the proof. Namely, we really construct a solution as follows, namely let B be a standard n-dimensional, or in this case one-dimensional Brownian motion. And given the vector field, we can just produce a martingale, which is obtained by integrating this function V when evaluated on Bs against Bs itself. So that's a stochastic integral of a measurable function with respect to Brownian motion. So therefore that thing M is a martingale. And then we consider the corresponding de Leon-Dart exponential of this martingale. So the corresponding exponential martingale. And then we write this Bs process, which was our starting process. We write this as a V, so we write this as a stochastic integral, or we add and subtract a stochastic integral. In infinitesimal writing, we write this accordingly, that dBs we write as a Vbs ds plus the old dBs minus Vbs ds. So it's just adding and subtracting this stochastic integral of V against ds. And for the second sum, or for the second two terms here, we just write them all together as a dW, in a similar fashion as we did for the Black-Scholes model. But okay, here's another dW that appears, where dW is a dB minus V of Bs ds, and of course we see that by the associativity of the bracket, this stochastic integral of V against ds can also be understood as the bracket process of this new martingale M with the B process, with the Brownian motion. And then we know by Gazanov theorem that this dW process is a Brownian motion if we change the probability measure. Namely, we introduced a new measure Q by means of a radon-Nikodym density, which is the de Leon-Dart exponential given the measure M. And this then altogether says what? That this pair of processes B and W, which is defined on the same probability, on the same measurable space that we started with, but now equipped with this new measure Q, this then in fact is a weak solution where W tilde is a Brownian motion. Why so? Well, obviously we have managed to write the dBs as a V of Bs ds times dW, where W is a Brownian motion on some probability space. So therefore we have obtained a solution. We have obtained a pair of processes B and W, where W is a Brownian motion, and B satisfies the stochastic differential equation in the sense that we have just discussed. Okay, now what about the question whether this is a strong solution? Well, if you look at the construction here, you start with the B and then you construct the W. So therefore, obviously, here the W is a function of the B. So the measurability is in inverse direction as you would want to have it. So the W is obtained in a constructive fashion from B by perturbing the B trajectories through a stochastic integral, which is obtained from B. So therefore, this W thing is something which is really obtained by applying a map from the B trajectories to obtain the W trajectories. But it's not in any way the other way around, that the solution trajectories B, which we will are adapted, are generated from the W trajectories. So in the general case for arbitrary V, this will not be possible to recover the B trajectories from the W trajectories. So therefore B is in general not a strong solution given omega tilde. So why would you ask for such a weaker notion of solution at all? Well, sometimes you're not really interested in this input-output mechanism or in the preservation of this input-output mechanism, but you're just interested in the statistical behavior of the process that comes out of such a description. And that's the basis for the next definition, namely, you say that a stochastic differential equation which has data V and sigma, we call that this stochastic differential equation is unique in law, or the solutions are unique in law, if it is true that for any pair of solutions x omega or xw and x prime w prime, if you have any weak solutions, any two for instance, which might be defined on different probability spaces, which might be obtained from different constructions and might not be related at all, but if the corresponding second components of these pairs of solutions are Brownian motions in this case, namely n or d-dimensional Brownian motion, if then it must necessarily hold that the two laws are the same of the x processes, the x and x prime processes, then we call the stochastic differential equation unique in law. So it says the following: if it is saying the following, if it is so that whenever you have a pair of solutions x or x and w, where the statistics of the w are the one you want, and if it is so that the resulting output statistics are uniquely determined, then you call this stochastic differential equation unique in law. And as an example for such a situation, I want to come back to this example before, namely if we have a bounded vector field in d dimensions, say, then this perturbation of the dynamical system given by V through a Brownian motion of the same dimension, then this is unique in law. So we have seen that we cannot, well, probably we can, but we have not yet seen how to obtain strong solutions for this equation. We have to see how we can obtain weak solutions for this equation. And I will now state that whether or not there is whether I have strong solutions or not, any weak solution of this equation, any weak solution x of this equation, provided I can identify such a process as a weak solution with some Brownian motion W, then this solution of this equation has a unique statistical description, has unique statistical properties, which is to say it has a unique law. Any two solutions to such a stochastic differential equation are equal in law. We give a sketch of this result, again in the special case of dimension 1. Namely, we assume we have a solution, any solution to that stochastic differential equation. So a pair of processes omega and x that satisfy this equation in the corresponding integral sense. Then we introduce another martingale, which is obtained by integrating the V process along the trajectories of the solution process x against the driving signal omega, against the driving Brownian motion. And again, we introduce the de Leon-Dart exponential, which is associated with the negative of this martingale. If we then rewrite this equation for dx as a dw, where we write dw as the dw tilde, where we write dx as dw tilde, where dw tilde is dw minus the bracket of the negative of this martingale m and the w process, which is just another way of rewriting the initial stochastic differential equation. We have represented the x process in such a way that it appears as a Brownian motion under the new measure q, which is obtained from p through the Radon-Nikodym density, which is obtained as the de Leon-Dart exponential of the negative of this martingale m. That's again a consequence of the Gazanov theorem. Now, if we ask for the finite dimension or for the distribution of the solution process x, we can test this as usual by looking at the finite dimensional distributions of the solution process, and this is obtained by evaluating all kinds of such expectations under the measure p of the evaluation of the x process at different times. So whenever we are able to compute such an expectation for all possible time points, then we have the complete information about the law of the process x. And of course we can insert the factor 1 in front of this product of random variable or evaluations by the ratio of the Radon-Nikodym derivative with itself. But the enumerator is now understood as the Radon-Nikodym derivative that converts the p integral into a q integral. So if I write it as a q integral, then this z in the enumerator is replaced by a 1. And in the denominator, I have this exponential martingale of minus m. If I write out what this is, this inverse of this exponential martingale, well, I just write out the definition of this de Leon-Dart exponential. It's the martingale itself, the minus the martingale itself, plus, because of the inversion of the minus term here, it's plus 1/2 times the corresponding bracket process of this process, but the bracket process of this process by, if you like, Ito symmetry or something, is v squared against ds. Now, I recall that the dws can also be written through a dxs minus v of x ds. This is just rewriting the stochastic differential equation that holds for x, which allows me to write the dw through this sum of stochastic integrals. And if I insert this into the stochastic integral here on the left-hand side, I see that I obtain an integral against the x process minus the integral of v squared against the ds, which is exactly the term which appeared here already, but with a plus 1/2. So altogether this generates a minus 1/2. and I see that I have just the de Leon dot exponential that is obtained, or is the de Leon dot exponential of this stochastic process, which is obtained by integrating the v process against the x process. Okay, so in the end I have under Q the de Leon dot exponential of the stochastic integral of v against x. That's now remaining, and that's as a factor in front of these product of different evaluations. But I have just said that under Q the x process is a Brownian motion. So altogether, this evaluation which I have here inside the expectation is just some more or less complicated path functional, which is evaluated on the trajectories of the x process, where under the Q measure, the x process is a Brownian motion, which in the end tells me that this expectation that I have to compute is an expectation which involves just the Brownian motion and just the information about just this x process, the transformation of the x process through this stochastic de Leon exponential, and the evaluation. So therefore, this expectation that I started with is uniquely determined through the requirement that the driving signal was a Brownian motion, and through the information about the v vector field. So in particular, I have convinced myself that this stochastic differential equation is unique in law. Now I introduce another concept of uniqueness, which is pathwise uniqueness, which is asking for more than just the uniqueness in law. It asks whether the trajectories, the solution trajectories, given a weak solution, whether then I have a unique trajectory that might solve the process, might solve the equation. So here's the correct definition. We have, as usual, some stochastic differential equation given through the data in form of a vector field V and a volatility or diffusivity matrix sigma. Then this equation is said to be pathwise unique. Pathwise unique now if whenever we have two solutions on the same probability space which are driven by the same stochastic process omega as driving signal, if then necessarily it must follow that the two solution processes that are almost surely identical on a path by path basis. So once more, we say the solution or the SD is pathwise unique if it is so that whenever we have two weak solutions which happen to be defined on the same probability space with the same driving signal process omega, then it must be that the two solution processes are really the same in the sense that the trajectories coincide almost surely. Okay. To ask for pathwise uniqueness is a stronger requirement than to ask for uniqueness in law. So we may have, in fact, a situation when the stochastic differential equation is unique in law, but not pathwise unique. I present one such example. The example is chosen by solving the stochastic differential equation without a drift now, and it's dx, that is supposed to be the signum of x times dw, where the signum function is defined on the real line. The whole example is in one dimension. So the signum of a certain number is defined to be just positive if the number is strictly positive, and else it's -1. So this signum function here, which I choose here, is the signum function that assigns only values +1 and -1, and the +1 is reserved for the strict positive axis. That's a certain function, and in one dimension, of course, I can understand it as a matrix-valued function, where, of course, matrices here are just scalars, and I can ask for solutions to this stochastic differential equation, which is now a stochastic differential equation where I have a non-trivial sigma, really a state-dependent sigma, but I have a constant vector field, or as even a vector field 0 in front. Okay, I want to show now that this stochastic differential equation is solvable, and it's unique in law, but not pathwise unique. Namely, first, we want to show that it is really pathwise unique, namely, unique in law. So suppose you have a solution to this equation. Then, obviously, this solution process is a martingale, because it's just a stochastic integral of some process against a martingale. And therefore, it must be martingale. It has continuous trajectories because it solves this integral equation, so therefore, it must be necessarily a continuous process. And the bracket process, by our usual rules for the bracket process of this process, will be the integral of the sigma squared function, the square of this volatility function, integrated against time. But the square of this volatility function is the identity function. So therefore, this integral against time is just t alone. And therefore, by the Levy characterization, we know that the solution process x must be a Brownian motion. So therefore, any solution is in fact a Brownian motion, and therefore we have uniqueness in law. Now let x be, and now I want to show that we don't have uniqueness in the pathwise sense, namely let x now be a Brownian motion, any Brownian motion, and let wt be the stochastic integral of the signum function against that Brownian motion. Then wt is again a Brownian motion by the same argument as above, because it's a martingale with that with the volatility, or with the bracket 1. Or t as identity function on the unit interval, on the time interval. Now, I can write that dw is, by definition, this sign of s of xs dxs, and I can just flip the sign function, and also write this in a way that is dxs is then the sign of dws, which means that the pair x and omega is a weak solution to this equation. Okay, starting from that equation again, that dxs equals sine xs dws, I can multiply this equality just by a -1. So I obtain that minus dx is minus the sine of xs dws. And this I can also write that the differential of minus x equals the sine of minus x s dws, because this sine function that I have just chosen is an anti-symmetric function, which means that I can just pull the minus sign inside the sine function. Of course, the sine function that I've chosen here is not exactly anti-symmetric. There is one point where the anti-symmetry is broken. That's the point when x equals 0. But that does not play any role, because the total time that the process x spends on the position 0 is 0 in expectation, which, since the process x is a Brownian motion, after all, it does spend 0 time at the location t equals 0, x equals 0. So therefore, this point of non-anti-symmetric behavior of the sine function does not play a role, and therefore I have convinced myself that also the process minus x omega is also a weak solution. So therefore I have two weak solutions which are defined on the same probability space, x and minus x, but obviously they are not the same. X is never minus x. So this stochastic differential equation is absolutely not unique in the pathwise sense, has no pathwise uniqueness. So we conclude this example by collecting what we have understood. This equation here is unique in law, but it has no pathwise uniqueness property. And as a remark, which is a little exercise, of course, it holds that pathwise uniqueness implies uniqueness in law. So asking for pathwise uniqueness is really more. And we have a little theorem now, which is the second of the three main theorems of this lecture today, which gives a condition, one already reasonable condition under which we do have, in fact, pathwise uniqueness. And this goes like follows. So if we have a stochastic differential equation in the form that we discussed now, with a vector field V and a matrix field sigma, and if we are in the situation that there is some constant such that we have this type of, as it's sometimes called, one-sided Lipschitz condition. So we have that the matrix field sigma satisfies this Lipschitz condition with respect to the spatial position where we evaluate the difference of matrices in the Hilbert-Schmidt norm. And if we additionally perturb this Lipschitz property of the sigma field by this, what is sometimes called monotonicity or dissipativity condition on the vector field, which is as a vector valued generalization of a monotonicity property of a function v. So function v is monotone if these products of these differences has a sign, and that's for the scalar case, and for the vector valued case we replace the pointwise multiplication by the inner product. This is what is called a monotonicity or dissipativity condition on the vector field. So we combine the dissipativity condition on the vector field, which is basically the ODE part of the differential equation, stochastic differential equation, and we add to that this squared of the Hilbert-Schmidt norm of the difference of the matrices sigma, which we obtain by evaluating sigma at different time points, correction at different space points x and y. If that joint expression is no bigger than some constant times x minus y, then, and we will see in a minute that there is a mistake here. Here we have, of course, the square on the right-hand side. So if that condition is correct, then the stochastic differential equation that we built with these data sigma and v is in fact pathwise unique. Okay, why is that correct? Well, we sketch again the proof only in dimensions n equals 1 equals d. And let x and x prime be two solutions which are driven by the same Brownian motion. Then I consider the difference process of the two. Now the difference of the two processes then satisfies just by subtraction of the two respective differential equations. It satisfies this equation in the sense of an integral equation that involves stochastic integrals. So therefore I can also use now the Ito formula, or the product rule, the corrected Leibniz rule for the stochastic, for the product of the square of the z process with itself. So I obtain 2 times z against z integrated plus the bracket of process of z with itself. Okay, now I insert what I know about the dz in this first part. The dz comes with 2 components, with a dt and a dw component. The z is the difference of the two, x and x prime, and that is then multiplied with the dt part of the dz, and then it is integrated with against the dw part of the dz. These are these 2 parts here, these 2 components of the infinitesimal infinitesimal increment of the z process, and then the Ito correction term is the bracket of z with itself, but as usual by the associativity of the bracket process we can pull out the factors which are in front, and here in the bracket they will pulled out in a quadratic form, which is then this difference squared times the bracket of w with itself, which is the dt. Okay, now comes our dissipativity or one-sided Lipschitz condition into play. Namely, if we isolate the parts which come with a dt, I see that exactly this combination of this one-sided Lipschitz or monotonicity condition of the v function together with the with the difference squared of the sigma matrix at these two different positions appears on the right hand side, and by assumption I can estimate these components by this product by the difference of the x positions squared times dt. And then of course the stochastic integral with respect to the Brownian motion remains. Okay, that's an inequality of stochastic processes, of real-valued stochastic processes. So I can hit this inequality with the expectation operation, which tells me that the expectation of zt squared is less or equal to the integral of the same function zt squared against the time dt plus the initial position. And if I call this function as a real-valued function in time, psi t, I find that psi t is less or equal than psi of naught in this case, which is 0 plus this integral of integral of psi against that time interval. So I'm observing this inequality, which is an equality for this function of time, which is defined as the expected value of the difference process at time t. That's an equality that's correct for any t non-negative. And by Gronwall lemma, I know that's a Gronwall lemma from standard ODE theory. If I have such a relation, then the function psi t can grow at most at an exponential rate, where c is this exponential growth factor. So in particular, I have this growth bound for the function psi, which involves in particular the initial value of the function psi. But in our case, since the z processes start at the same, so since the x and x prime processes start at the same initial condition, the z at 0 is 0, or the psi is even 0, and therefore the whole psi function at any time t must be 0. Therefore we have uniqueness in law. Okay, so if we have this one-sided Lipschitz or monotonicity condition, which is met or is combined with this Lipschitz condition on the diffusion matrix, if that's, as we shall in the future say, one-sided Lipschitz condition is satisfied, then we have uniqueness in pathwise sense of the solutions to this equation. A side remark: the Hilbert-Schmidt norm of a matrix is basically, or squared is basically the analog of the Euclidean norm for a vector. You just square all entries and sum that up. That's the square of the Hilbert-Schmidt matrix, Hilbert-Schmidt norm. And the final theorem, the final big theorem of today, and therefore of this whole semester, is the statement about the strong existence of solutions to stochastic differential equations under global Lipschitz conditions. And the statement here is as follows. So we will require now more on the coefficients on the stochastic differential equation in order to guarantee that we have existence in the strong sense of solutions. I want to point out that the condition that I formulate here below are only so that they already give some reasonable field of application, so it's kind of already not totally empty theorem in terms of its scope, yet the proof is still acceptable in its on the level of its how complicated it is. But the truth is that the strong well-posedness result for stochastic differential equations nowadays goes much beyond this, the conditions that are being formulated here. What I want to say is that the conditions here, which I formulated now below, can be relaxed dramatically, and still the result is true that we have global well-posedness, global strong well-posedness of solutions to stochastic differential equations. Okay, but let's give now at least one theorem, which is non-trivial and which is accessible by the means that we have, by the mathematical toolbox that we have so far developed. Okay, so the conditions are as follows. We want to consider a stochastic differential equation driven by a vector field V and driven by a Brownian motion in d dimension with a diffusivity matrix sigma. And we want to assume now global Lipschitz and growth conditions, so we want that the vector field V is Lipschitz, is globally Lipschitz, and we want that the sigma matrix function is also globally Lipschitz with a certain Lipschitz constant k. That's the one condition, and the second condition that we want to impose is a growth condition, namely that v and sigma grow in the respective norms at most in a linear fashion, where we have some growth factor k, which is in front. So this k thing here, for instance, tells us that we don't care too much about the growth of these functions near the origin. So we are interested in the growth of these coefficients far outside, where it should not grow more than linearly with respect to the position where we evaluate. Then this stochastic differential equation, which is driven by white noise in dimension d with a specific any initial datum x, admits a unique strong solution given the Brownian motion omega. And moreover, we have an estimate which gives them bound on the second moment of the solution. Okay, so the proof is slightly involved, but not too much, and I want to give it again in dimension d equals n equals 1. The proof is based on a Picard iteration, similarly to the Picard-Lindler theorem that you know from ordinary differential theory. So we start with we construct a sequence of processes, which then in the end approach the solution, which is then giving the claim. Namely, we start with a constant process, which is just at the trajectories that stay in the position x. And then if we have constructed the sequence of processes up to sequence level k, then we define the level of k plus 1 process just as the corresponding quantity which are obtained by integrating the coefficients of the stochastic integral in the corresponding sense along the level about the lower level stochastic process x. So that's just this iterative procedure. The trajectories of the process level at level k plus 1 are obtained by feeding in the process at level k into the coefficients of the stochastic differential equation and just performing the stochastic integral there. And we fix, for the argument here, we fix a certain maximal terminal time on which we want to construct the process to start with. Okay, and then I claim that there is a certain constant c, which is independent on the process level approximation level k, such that the second moment of that process for any time in the interval from 0 to capital T is bounded by this constant times 1 plus the x norm, the squared of the initial position. Okay, we show this by induction. We start with k equals 0. Here is nothing to prove because the 0 level process is just a constant trajectory. And for the induction step, or for one ingredient of the induction step, I write down, or if I want to make an estimate, that gives me a bound on the size of xk plus 1. Given some information that I have on all the processes below, it is natural to consider this representation of the psi process. I just see that I made a mistake in the definition of the iterates of the process. Of course, I forgot to introduce the x initial condition for this in this constructive mechanism. Okay, so if I have this representation of the iteration of the process at level k plus 1, given the process at level k, of course, that's a good point to estimate then xk plus 1. So since I have represented xk plus 1 as a sum of 3 different ingredients. I can estimate the square of xk plus 1 basically through the square of all these ingredients, where I use the not suboptimal upper estimate that the square of the sum of three numbers is bounded from above by 3 times the square of each of these numbers, 3 times the sum of each of these numbers. Okay, so if I do that, and then I obtain that the expectation of x, so I do this inequality, which the pointwise inequality first, and then I hit this inequality with the expected value. So therefore, the expectation of xk plus 1 is bounded from above by the 3 times the initial condition squared plus 3 times the expectation of the deterministic or drift integral squared plus 3 times the expectation of the stochastic integral squared. That's the upper bound, the first step. Then in the integral of the ds part, I perform a Cauchy-Schwarz inequality with the identity function 1 in order to move the square operation inside the time integral, which gives me an additional factor t in front, but then I have the v square inside this time integral. And for the computation of the expectation of the stochastic integral squared, I use the Ito isometry, which tells me that the expectation of a stochastic integral at a certain time is just as good as the stochastic integral squared at a certain time is just as good as if I take the bracket process at that time, and the bracket process here is just this integral against the ds. Of course, all this is inside the expectation. Then I use my induction hypothesis that this XS correction is not quite correct. What I do now is that I use the fact that I use the fact that both the V and the let me see it again. Okay, I need to make a short break, sorry. Right, so here if I this is where we got so far, and I want to estimate this now from above, and this is where my growth condition on the coefficients v and sigma will be used. I wanted to assume that both v and sigma in norm grow no more than linearly with the growth factor k, and then I have this 1 plus x as the growth factor on the right hand side. I have v and sigma here both appearing with a square, so therefore I can estimate these squares by the square of the upper bound from the hypothesis of the theorem, which produces this 1 plus x and so forth to the power 2, and I have used this upper bound 2 times, and namely 1 time for the t part, for this integral which comes with the t, and another time just alone. So therefore I am having this additional bracket of t plus 1 after I collect the terms and factor that out. Okay, and then I can compute this, I can take the bracket here, or compute this, estimate this from above by twice the square of each of the components, which generates to me, if I do the integral, this additional term coming from the 1 factor, and I'm having the s squared alone here. And all this can be then condensed into an estimate which collects an integral which involves the square of the x process at level k plus everything else, which is some constant in the end, plus the x naught squared, which altogether can be estimated from above by picking a proper constant c naught tilde, which is assumed to be larger than 1, so that I can estimate all these things on the right hand side by this C naught tilde times 1 plus x naught squared plus a C naught, the same C naught tilde times the expectation of this xs process when I integrate, xs process squared when I integrate from 0 to t. So this is already pretty close to a Gronwall type inequality, so an inequality of a similar type that we had seen before, although it is not yet quite a Gronwall inequality because I have these different levels of approximation which appear on the left and on the right hand side. And so therefore the game is now to iterate this not yet fully Gronwall inequality in order to obtain in the end still the desired exponential upper bound for the x processes. So I'm doing this as follows. I know, of course, that the x naught process and expectation is bounded from above by the initial condition x naught alone. And here I should probably write just the x, but okay. And then I can use this inequality, which I have just obtained in an iterative fashion. Namely, I know then that xt1 squared at any time between 0 and capital T, this expectation is bounded from above using just the previous inequality by this constant times C naught tilde times the integral of the previous level process, which in this case was just the x naught squared, just a constant. So doing the integral, I obtain this. And this, of course, can also be written or can be estimated further from above by just pulling the C naught factor in front and writing this as a C naught 1 plus x naught squared times 1 plus C naught tilde times t. Okay, and I claim now that in an iterative fashion the following estimate is correct, that the expectation of xt(k), so the kth level process evaluated at time t, taking the square of this and the expectation of that is bounded from above by this joint factor C naught tilde 1 plus x naught squared times this finite piece of the exponential sum, which you see here. So it's just this partial sum of the exponential function. And okay, I probably spare the details. It's just inserting this this inequality, which is my basis inequality, which needs to be iterated. So that's my base inequality, which I use for the induction step. And if I start from the induction hypothesis that this inequality is correct, and I insert this inequality, this upper bound for the process at the lower level into the leading inequality, then I see that I have to take an integral over this finite partial sum for the exponential function, which together with the terms which come in front generate to me the partial sum of the exponential function at one level higher. So that's just a little bit of algebra that we can do. So therefore we convince ourselves that this claim here is actually really true. That was an induction argument. And of course this partial sum of the exponential function can then be upper bounded by the exponential function alone, which ultimately gives me this estimate for any level of this approximation k, that this expectation of this the square of the process at time t is bounded from above by this exponential number, which is good to know. And in an analogous, so this establishes this exponential bound, or this correction, this bound for the second moment. And in an analogous fashion, I can now, or in this kind of similar spirit, I can now look at the difference process of two levels of approximation. And okay, writing down the difference of two levels of approximation, I see that in the difference of the corresponding stochastic differential equations, I have effectively the difference of the processes at one level below appearing, obviously, by the recursive structure of this Pika iteration. And if I write these two terms which represent the difference process on level k plus 1 and k as an ak and mk, then I can estimate in a separate fashion using the assumed Lipschitz continuity of the v and the sigma coefficients of the matrix as follows, namely the expectation of the supremum of this ds integral squared. This supremum on the of this integral here is again by an L2 Hölder inequality with respect, or Cauchy-Schwarz inequality with respect to the time, can again be estimated from above by the square of the difference of the processes one level below, integrated against time from the interval from 0 to t, where I have used the fact that the v function is Lipschitz continuous, so that this difference of these two evaluations of the Lipschitz function is bounded from above in absolute value by the difference of the two positions. Regarding the maximum of the stochastic integral part, I can use the dupe maximum inequality, because it's in, if I want to compute the expected value of the maximum of the stochastic integral, this is exactly a situation when I can use the dupe inequality, which tells me that the expectation of the maximum of the stochastic integral of this integral squared can be estimated by a constant which is universal times the expected value of this integral, so this correction of this martingale at terminal time in the power 2 in this case, and the expected value of the stochastic integral at certain time here is then by E2 isometry given again by the time integral of the integrand squared, which is just a representation of this bracket process. And here then I finally see how the Lipschitz continuity of the sigma really kicks in, because then I have an integral over the Lipschitz over the difference of the sigmas in a ds integral, where I can insert straight away the Lipschitz continuity of the sigmas and arrive at this inequality. So altogether, if I put this all together, this finally tells me that I can estimate the expectation of the supremum of the two processes xk plus 1 and xk on the time from 0 to little t by a certain constant which depends only on the number capital T, on the maximum time index or time parameter on which I want to do this whole analysis, times the integral from 0 to t of the stochastic of the difference of the processes one level below. So you see that on the left hand side you have the supremum, on the right hand side you have the integral, and then you can recursively again iterate this inequality. Again, this is a little bit of algebra which ultimately yields the claim that the expectation of this supremum of the difference of the two processes for two consecutive levels of approximation here at level k is bounded from above by effectively a function which is a piece of the exponential series. And it's if t is my maximal parameter, then I have that this is bounded from above by a certain constant times t to the k over k factorial. Okay, that's a bound on the expectation of this difference of these two approximating levels on the time interval from 0 to t. This is correct also if I pass to little t being equal to capital T, and ultimately I can use this for a Chebyshev type argument, namely if I ask what's the probability that these two different levels have a deviation on the time interval from 0 to t by more than 1 over 2k, then using Chebyshev inequality, I'm picking up the expectation of this quantity squared, which is here on the right hand side, if I can bound that from above, times this threshold inverse to the power squared. This is then the 4 to the power k. And if I call this number on the right hand side alpha k, then since these alpha k's are summable, namely their sum is the exponential function at this position, by Borel-Contelli I can conclude that this event, this sequence of event has only a trivial or a zero lim inf event, which means that this deviation will be observed only finitely many times, almost surely, which again, by the summability of these coefficients here, of these tolerance thresholds, tells me that this sequence here of trajectories is almost surely a Cauchy sequence in the set of continuous trajectories on the time interval from 0 to t. So therefore there's a continuous process, which is the limit process of this sequence of approximations. It's a convergence which holds true uniformly on the time interval from 0 to t, almost surely. In particular, this limit process is a continuous process. And finally, I can now argue that this limit process is actually a solution to the stochastic differential equation, because on the approximating level, on each of these approximations, I have the corresponding recursive formula, and I see that while here we have still different indices, if I pass to the limit for k to infinity, then formally all the indices converge to this index infinity. But that's not enough. What I really need to use here is, again, a version of dominated convergence for stochastic integrals, which means that by continuity of sigma and v, when the trajectories xk converge, then do so also the corresponding coefficients or the integrands here in these stochastic integrals. So by my favorite version of dominated convergence, I can conclude that also I can pass to the limits in the stochastic integrals that I have here on the right hand side. On the left hand side I have the convergence towards the x infinity anyway. So therefore I'm arriving at the desired equality, which tells me that the limit process x infinity is in fact the solution to the stochastic differential equation. Moreover, the xk processes, all that I can easily show by induction, are all measurable with respect to the filtration which is generated by the process W, and so is also the pathwise uniform limit x infinity. So therefore this x infinity process is also adapted to the filtration generated by the W process. This settles the well-posedness of the solutions to this equation in the strong sense, at least on the time interval from 0 to t, where capital T it was an arbitrary number, and I can either argue that I can have these trajectories on any fixed time interval of arbitrary big size, which is one way to say that I have trajectories up to every time I wish, or I can also argue by iteratively applying the previous argument to these finite intervals when I restart the argument at the terminal value, which is then the random variable, but nevertheless the argument will be the same, from which I can start as new initial condition the trajectories on this new time interval from t to 2t, and then I iterate, which then produces me these trajectories of infinite on the infinite time axis. Okay, so this settles in a way the final main theorem of this lecture, which tells us that If our coefficients are not too bad, then we can really define in a rigorous fashion what we understand by a solution to a stochastic differential equation for more than just linear or whatever data. And of course now there is an enormous playing ground by which you can try to model different phenomena, because depending on the choices of coefficients v and sigma that you make, you will have really big differences in the behavior of the corresponding solution trajectories. So this is really now a huge field for models, and also for analysis. But if you are not so much interested in really the probabilistic side alone, the final proposition of this lecture in this semester will be the connection between stochastic differential equation and partial differential equations, which I will formulate here also under probably very strict conditions, but I do so in order to have a most simple presentation for the purpose of highlighting the main mechanism. Okay, the next proposition, and again is the final one, makes this connection between stochastic differential equations and partial differential equations, which we had seen basically already in the case of Brownian motion, but now we can extend this significantly to a larger class of to partial differential equations. So the formulation that I want to give here would be as follows. So suppose you have a real valued function u, just now a deterministic function, just as you know from analysis of PDE. You suppose you have a smooth function which satisfies a smooth function in time and space, which satisfies the following parabolic differential equation, namely the time derivative of u equals the gradient of u times a vector field v, where v is a datum, and then there is a second order component, which is a recombination of the second order derivatives of u in the different coordinate directions, but they are reassembled by means of a certain matrix, which is obtained as a matrix sigma transpose, which is well, in a way, this is just if you look at this, you would see as a PDE person, you would see a linear second order operator in non-divergence form with a certain constant matrix in front of the second order part. Okay, so and here we want to assume that the second order part can be written, the matrix in front of the second order derivatives can be written as the matrix sigma transpose sigma, where sigma is a matrix of a certain dimensionality. And so we want to assume that U satisfies this assumption, this parabolic PDE, which is a generalization of the heat equation with a certain initial condition in a function U. And then the connection to our theory of stochastic differential equation is as follows, namely let x omega be a possibly weak solution to the stochastic differential equation, which is obtained by using this vector field v, which appeared in this elliptic operator, and using this matrix sigma, which appeared in the representation of the non-divergence second order part. So if I have a solution to this stochastic differential equation, which starts at position x naught, or x, then I can represent the solution to this PDE just by plugging into the initial condition of this PDE the solution of this stochastic differential equation at time t, which was started at position x. So the solution of this PDE has this probabilistic representation, where on the right-hand side, the only things that enter, or the things that enter and which I obtain from the PDE, are of course the initial condition of the PDE, and also the solution x of a stochastic differential equation, which uses the data of the PDE in order to generate this random trajectories. Okay, here you see that in order to, so you could interpret this statement of this proposition as a way to construct effectively the solutions of a PDE by means of solving an ordinary differential equation and then propagating the initial condition of that PDE by means of these trajectories. That is then the right representation of the solution to this PDE. So in this regard, you could say I can solve this PDE by just solving an ordinary differential equation. And I will comment on this a little later. The proof of this will be short if you are able to work with the Ito formula, which you now can, and which we have learned how to do, and therefore I will sketch on the proof only. The trick is similar to what we did effectively in the Black-Scholes world before. The trick is here to assume that you have the solution and then to insert the process, but before you insert the process, you invert the time inside the time parameter of the solution. So that's what we do here. So we introduce a new process, psi s, which is a process which will run on the time interval from 0 to little t, and we assume that you have the solution of this stochastic differential equations. We assume we have the u function, the solution of the PDE, and therefore we can produce a new real valued process by inserting the SDE solution into the PDE solution, but we will invert the time in the PDE solution. So that's the new process. It's a process in time, which is produced by inserting into a certain function two variables, two processes, namely a time process and a stochastic process. And so the Ito formula is available to such a situation if you assume that U is smooth. So using the Ito formula and doing the algebra, using the stochastic differential equation for star, that's very similar to what we did already in the case of the Black-Scholes stochastic differential, Black-Scholes PDE. We find that this function, that this process psi, is in fact a martingale. That's the critical observation, that this process, which involves the solution of the PDE, the solution of the SDE, and the time inversion, that this is a martingale. So fine, so a martingale has constant expected value, which means that the expected value of psi at initial time is the same as the expected value of psi at time t. What is psi at initial time? At initial time, psi is u at t minus 0, because s is 0. That's just the initial function. The initial, that's the solution of the PDE at time t. And at what is x at time 0? Well, that's the starting point, little x. So therefore, when the time parameter little s is set to be equal 0, then the psi variable is just deterministic and is u of t and x. That's a consequence of this time inversion. And what's psi at this psi process at time little t? Well, that's when s equals little t, I get the u at time 0, which is the initial condition of the PDE, so u naught, and I obtain the x process at time t. So therefore, the psi at time t is exactly this random variable of which I had the expectation. Okay, and therefore we arrive, you see, very quickly at this equality, which represents the solution of the PDE by means of a solution to a stochastic differential equation. And this is strongly reminiscent of the methods of characteristics that you might have known for a partial differential equation in which have at most one derivative. This is called the method of characteristics, by which you propagate the solution or the initial condition in order to construct solutions. And this method here can be understood as a method to produce second-order characteristics, but that involves the necessity to deal with not ordinary differential equations, but differential equations which involve randomness, but then we arrive at such representations. And from this you can see that the theory of stochastic differential equations and the theory of partial differential equations are very, very closely related. In some fashion, they are two sides of the same thing. Now, you can either study partial differential equations through the lens of stochastic differential equations, or you can also use PDE arguments in order to make statements about the properties of stochastic differential equations. So all this comes with this idea of second-order characteristics and gives rise to an enormous field of applications, modelization, and mathematical theory that you can study from now on. Okay, with this little bit of outlook, I conclude my final lecture in this semester. The next semester will be devoted to different fields of applications, mostly in physics, and I hope that some of you stay interested in this stuff. Thank you.